systematic program here at the Fields Institute, the Geometry and Model Theory seminar. This is our first meeting for the whole semester, and I'm very happy to welcome Adele Padgett from the University of California, Berkeley, to give the first talk. She will tell us about the very intriguing sounding sublogarithmic-transexponential series.
Hi, hi everybody. So yes, I'll talk about how to construct a field of sublogarithmic transexponential transseries today. And to start, I just have some background. So here for motivation, I have two results. First, Wilke's proof that the real numbers as an ordered field with exponentiation is model complete, from which you can show that it's O-minimal. And second, from Miller's paper, exponentiation is hard to avoid, the growth dichotomy theorem for O-minimal structures. So the growth dichotomy theorem says that, well, if you have an expansion of the real numbers that's polynomially bounded, or we say that it's polynomially bounded if for every definable function f, there's some number n, such that for all large enough x, f of x is bounded by x to the n. And the theorem is that if r is O-minimal and not polynomially bounded, then the exponential function is definable in R. So it's natural to think about generalizing this definition to talk about exponentially bounded structures. So we say a structure is exponentially bounded if for every definable function for all large enough x, the function is bounded by some e to the e to the e to the e to the x. And then this leads to the question about whether there are any O-minimal structures that are not exponentially bounded. So we would say a structure that's not exponentially bounded is transexponential. So if you think the answer to this question is yes, you might try to build a transexponential structure. And the way you might do that is by taking the real numbers and expanding by a transexponential function. So a good candidate to try to make that work is this function constructed by Knesser. So he constructs a solution to this difference equation, which it's not too hard to see just by looking at it that a solution is going to be transexponential. And the solution Knesser constructs is also real analytic, which is a good sign if we want to try to use this function to build an O-minimal structure. So a long-term goal might be to show that Rnx with a new symbol for this function e is O-minimal. And to give an idea of how you might go about showing that, I've copied down this lemma from a paper of Vandendries, McIntyre, and Marker, in which they show that Rnx is O-minimal using some generalities about Hardy fields. And so this lemma shows how that comes into play. So the lemma says that if you have a theory of an expansion of the real numbers as an ordered field that has quantifier elimination, then the theory is O-minimal if and only if each term is eventually positive, is eventually zero, or is eventually negative. So I've labeled these 1 and 2 because this lemma gives like a two-part strategy for trying to show that a structure is O-minimal. So if we would want to try to use this lemma to show that Rnx with this new function e is O-minimal, you would first want to try to find a language in which its theory has quantifier elimination. So here I've listed out the symbols that you are already in the language. So the the language of ordered rings and restricted analytic functions and exp and e. To have quantifier elimination, you would need symbols also for the inverses of exp and e. So you probably want to add a symbol for log to your language, and I'll write L for the inverse of e. Now, the derivative of x is just x, so that you don't need to add a new symbol for that. But we will want to have symbols for the derivatives of e, because those are definable. And then we want to add also function symbols to represent the inverses of the derivatives. And then, well, you might think you need also symbols to represent the derivatives of these inverse functions, but you don't need that because it's just a little calculus trick. You can represent the derivative of an inverse function in terms of the function and the derivative of the original function in the inverse. So I haven't shown that this theory has quantifier elimination in this language, and I think it would probably be quite difficult to show that. But based on the work that I've done, I think it might be a reasonable language in which to try to prove quantifier elimination. But the work that I've actually spent time on is working through the second part of this two-part strategy. So looking at the germs at infinity of terms in this language. And so that was the reason why in my thesis, I built a field of sublogarithmic transexponential series. So the transseries field is built specifically so that it will embed the field of germs at infinity of terms in this language. And then because the field of transseries is ordered, it induces an order on the field of germs. And so then the field of germs is ordered. So this is what I meant in my abstract when I said that this construction could be seen as a one step toward maybe building a transexponential omnimal structure. So before I talk about the exponential or the sublogarithmic transexponential transseries construction, I just want to note that transseries constructions like this that involve transexponential that are transexponential are of independent interest. So I want to mention two other results also about building transexponential transseries. So first is this thesis of Schmeling, in which he and I think also van der Hoeven build fields of transseries that are closed under some countable ordinal iterates of log and exp. So countable ordinal iterate, what does that mean? Well, the first iterate of exp is just exp itself. The second one is exp of exp. The omegeth one is the function that I was calling e, or it satisfies a difference equation satisfied by the function I was calling e. And so actually there are many things that happen in this thesis, but one of which is the construction of transseries that are closed under some of these countable ordinal iterates of log and exp. And then more recently, just last year, Bagayoko, van der Hoeven, and Kaplan build a field of transseries that's closed under all ordinal iterates of exp and log. So they discuss in this paper, hyperserial fields, that the field of transseries that they build is not yet known to be a differential field. To solve this problem that comes from omnimality, you need to be able to order not only expressions involving E and L, but also its derivatives. So the field that I build, it will be a differential field because it needs to account for germs of these L terms involving the derivatives of E. It'll also be much less complete than both of these other trans-exponential transseries constructions. So now just a high-level overview of my talk and of the construction. So first I'll just gather some information, basic information from the difference equation here. And then the actual construction can be divided into 3 parts. The first part is to show that some relatively simple finite sums can be ordered in a way that reflects the actual ordering on germs of L terms. And then the second part is an adaptation of the usual logarithmic exponential transseries construction of Van den Dries, McIntyre, and Marker. So the construction is adapted so that instead of starting with an initial group of monomials that's the powers of x, we'll start with e of x monomials, and then end up with a field that's closed under x and log and restricted analytic functions. And in this part, this section 2, we'll use the ordering result from section 1 to make sure that the field that we build is ordered. And then part 3 is to start from the usual logarithmic exponential transseries and then actually build the full field of, actually build the full field of trans-exponential sublogarithmic transseries. So closing off under E and its derivatives and L. And it turns out that in the structure that we build, the inverses of the derivatives of E can be approximated just using E and the derivatives and L. So we only need to worry about E and the derivatives in L. And so this part 3 will involve doing the construction in part 2 lots and lots of times, and then building lots of these fields and putting them together. So first, just what are some basic things that we can deduce from the difference equation for E? So first, this one is pretty obvious, but E of x plus 1. This is, and all this will hold for all large enough x. I'm just thinking about the asymptotics. Will be bigger than E of x to the n for all natural numbers n. So second, if we look at the difference equation and we differentiate both sides, we get E prime of x plus 1 using the chain rule. We get x to v of x times E prime of x, and x to v of x is just E of x plus 1 itself. So we get this differential equation for the first derivative of E. And then you can continue differentiating. And the formula you get for the dth derivative of E at x plus 1 is E of x plus 1 times, E prime of x to the d choose 2, E prime of x to the d minus 2, E double prime, and then lots of other terms. The smallest one is ed of x. So this is a polynomial. It's actually the dth Bell polynomial with E prime up to the dth derivative substituted for its variables. And so you get a Bell polynomial here because you're just essentially doing a repeated chain rule. You're continuing to exponential or to differentiate x with E of x. Okay, so we get these differential equations for all the derivatives of E. So third, this is not too hard to show. E of x to the 1 plus r for any positive real number r will be bigger than the dth derivative of E. And lastly, for any d. So every E of x to the 1 plus r will be bigger than any derivative. And E of x plus c for a positive real number c will be bigger than any derivative to any power. So I'm writing these things down, not because I'll use them explicitly later in my talk, but just to give you the intuition that shifting inside of E gives you something that's much bigger than taking powers, and taking powers gives you something that's bigger than taking derivatives. So that's the intuition that you can keep in mind as you look at expressions and sort of get a sense of how large they are. Okay, so now now on to the first section of the construction. So this is an ordering result. We want to be able to order formal finite sums. And so first, just some intuition for how we'll be able to do that. So usually the ordering on a transseries is defined by, so you take a series, you look at the coefficient of its leading term, the leading monomial, and you check whether that's positive or negative. But this is not going to work for us. And I have a quick example to show why. So E of x, E double prime of x, we're gonna eventually want to think of this as a monomial. And this, you can do a quick calculation to show that this is bigger than E prime of x squared. But the finite sum, E of x, E double prime minus 2, E prime of x squared, this is actually going to be negative. So what this is saying is that even though E of x, E double prime is bigger as a monomial than E prime squared, it's not dominant. So subtracting off 2 times E prime of x squared is enough to bring the germ below 0. So a way to fix this comes from a paper of Bosher-Nitzan, actually that Lau mentioned last week, where Bosher-Nitzan studies Hardy fields and transexponential functions. So given a transexponential function, Bosher-Nitzan defines a sequence. So starting, the first element in the sequence of functions is just the transexponential function itself. And then you get later elements by taking logarithmic derivatives. And the reason why this sequence of functions is useful is that the dth derivative, each dth derivative can be expressed as a polynomial in the first d+1 elements of the sequence. And second, each element of the sequence is bigger than any power of the next element. So using these two facts, we can rewrite this short finite sum here. And I'll just, it's a little bit of a calculation, but I'll just jump to the end. You get E0 of x squared, E1, negative E0 of x squared, E1 of x squared, plus E0 of x squared, E1 of x, E2 of x. Using this second condition, you can see that this one is the leading monomial. This monomial is larger than the other one, and it's also, it dominates. So its coefficient, which is negative, should decide the sign of this sum, and it does, because the sum is negative. Okay, so that's kind of some intuition that comes just from working with germs of functions that we'll use to figure out how to order the formal objects that we build. So first, a little bit of notation. So for us, K will be an ordered field, and it's where our coefficients and exponents will come from. In X, we want to think of it as a set of formal variables. In a little bit, we'll want to be able to bound the distance between elements of X and also subtract natural numbers from elements of X. So we want to think of X as a set living in some ordered field. So now let G, which will be our group of monomials, be the multiplicative abelian group generated by formal symbols of the form be d of x to the a. Now this, I'm saying it's a formal symbol, and I'm writing still like the e notation to indicate where it comes from. But we really want to think of these as formal objects and impose the structure on them. And then the goal of this section 1, is to show that this group ring, which we'll call the E sums, is ordered. So monomials from G and coefficients from K. Now, the second definition, let H be, and I'm going to explain what I mean by lexicographically ordered, be the multiplicative abelian group generated by now symbols of this form. So we want to think of these as being based on the sequence of functions from Boucher-Nitzan. Now, before I fill in the rest of this definition, so this group H is lexicographically ordered. So what I mean by that, it's ordered by looking at these indices. We want to use this fact here for our ordering. So any element of the sequence should be larger than any power of the one that comes after it. And also, X is an ordered set. So we want to think of if X is bigger than Y, two elements of X and Y, and X is bigger. We want to think of any generator coming from X to be bigger than any generator coming from Y. So that's the way in which H is ordered. And then because H is an ordered group, we can define the Hahn series field with coefficients in K and monomials from H. So now, like I said, H is a purely formal object, but we want the ordering we've defined on it to actually match the true ordering that comes from germs of functions. And in order for that to really be true, we need to make some assumptions about the field X and the set K. So first, we want E of X for any X and X to be bigger than the field of coefficients K. And that makes sense. We want our monomials to be bigger than the field of coefficients. But then I also have this, I have this shifted by M term because eventually we're going to want to have logarithmic and exponential structure on these monomials. And so we'll think of X minus M as being like log of log of log of log of E of X. That just comes from the difference equation for E. And we still want monomials that look like this, log of log of log of E of X. We want these to still be bigger than our field of coefficients. Now, this second assumption, this is really just saying, so if X is bigger than Y, then we're justified in saying that any generator involving X is bigger than any generator involving Y. So we assume that that's true, so it makes sense to order H in that way. And the shifting by N is the same kind of thing. Eventually we'll want to have exponential or logarithmic structure. And then this last condition says basically that the elements of X are all bounded by something that's less than 1. So another way to think about this is that for all elements of X and Y, E of X has to be less than E of Y plus 1, because if X and Y differ by less than 1, so this has to be true. And eventually we'll want to think of E of Y plus 1 as X of E of Y. So what this condition here is really saying is that we want our generators to be less than exponentially far apart, so that once we start trying to close under X and log, we know we're starting with something that's kind of in the same exponential range from each other. Okay, so once we make these assumptions, we know that it's okay to order H in this lexicographic way that I've mentioned. And now, like I said, the goal of this section is to show that this group ring is ordered. And the intuition that we have is that we should somehow rewrite each element of this group ring in terms of one of these E star sums. So that's like rewriting some expression involving the derivatives of E in terms of the elements of Bose-Schmidt-Son's sequence. The way that you formalize that is by defining a map from the group ring to the Hahn series field, so that sigma of S should be defined intuitively as S somehow rewritten in terms of the elements of Bose-Schmidt-Son's sequence. So here I've shown how sigma should be defined on a generator of the form ed of x to the a. And then from there, you can extend it across products and sums. So the problem here is this exponent a. We know, I'm going to jump back for a second. We know that ed of x can be expressed as a polynomial in the first d+1 elements of Bose-Schmidt-Son sequence. So we're just going to define, or we would like to define sigma on ed of x without the exponent a, just as a polynomial. So that's what I've written out here. So the leading term of the polynomial is e0 of x times e1 of x to the d plus some smaller terms. And we want to make sense of exponentiating or having that to the power of a. So we factor out this largest term, and then we get the leading monomial times this thing. And this thing that I've underlined here, you can expand, make sense of as an infinite sum. And so here is the actual definition in the last line, and this is an actual element of the Hahn series field. So I'm doing this computation just to give you a sense of how you would define this map sigma. So in order for sigma to actually work, like, okay, you take some elements of the group ring and rewrite it, you need to know that sigma will be injective. And that's the main result of this section. So if x and k satisfy the assumptions in blue above, then sigma will be injective. And so then we know that the order on the Hahn series field induces an order on the group ring because sigma is injective. And because we defined, because of our assumptions, the Hahn series field really does match the ordering that comes from true germs of functions, so will the induced order on this group ring. And so the point of this, the purpose of thinking about finite sums, is that later on, when I talk about how to build infinite series, we won't anymore have like a notion of a dominant monomial, but we will have a dominant leading finite sum. So you'll take your series, you'll look at its dominant finite sum, use this lemma to determine whether that sum is positive or negative, and that will tell you how the sign of that will tell you the sign of the series. Okay, so now the second section is how to adapt the usual logarithmic exponential transseries construction due to Van den Dries, McIntyre, and Marker. So here it's delicate, but I've sort of written out a quick summary. So you start with a few, okay, so K is an exponential ordered exponential field. And so you start with the Hahn series with coefficients from K, and your starting group of monomials is the powers of X. So the construction can be divided into two sections. So the first part is to inductively add new larger monomials to close off under X. And so just to be a little bit more precise about how this works, so at stage n, you've built some field Kn, and you can think of any element of the field as separated into its infinite part plus its finite part plus its infinitesimal part relative to the thing that came before. And then your stage n+1 field is the Hahn series field now with the field Kn as its coefficients, where you add new monomials for x bit x of all the purely infinite elements. So where A here is the elements of Kn, who you say their support is greater than 1. So this, for example, this S infinity, the purely infinite part, its support is greater than 1. So then they iterate this construction closing off under x, and they end up with an exponential field. So that's the first part. And in the second part, they define this self-embedding so that for each element of the exponential field they build in part 1, the image under the embedding has a logarithm. And then they keep embedding the field into itself and take a direct limit and end up with a field that's closed under x and log. So I'm reviewing this just as a point of contrast with what I'm about to do, or to show how it can be adapted. So what will go wrong if we just naively start with the group G, which, remember, G was generated by things like this. So if instead of starting with the powers of x, if we try to start with G as our starting group of monomials, so there are several things that go wrong. First, a logarithm of e prime is not naturally going to arise. I think I might skip these things and come back to them if there's time at the end. Second, some monomials of G will be small relative to other ones. But the biggest problem is that G has reverse well-ordered subsets of monomials that are all very close together. So the question is, what do we do about sums like this? E of x to the 1 over n, e prime of x to the 2 minus 2 over n, e double prime of x to the 1 over n, and Cn are just some coefficients. So what's the problem here with this series? Well, when n equals 1, the monomial we get is e of x times e double prime of x. So remember from our earlier example, that's this monomial. And then as n gets bigger, the contribution to the monomial of the e and e double prime terms decreases, and the contribution of the e prime squared term increases. So we are going to get a decreasing set of monomials. But the issue is that if we think of these now as functions, the limit as x goes to infinity of e of x, e double prime of x over e prime of x squared, this is actually going to be 1. So these monomials grow at very similar rates. This limit result also holds if you pick any two monomials of the sum. The limit of their quotient will be 1. So the question is, how do you make sense of a sum like this, where depending on how you choose these coefficients, you could have the partial sums jumping back and forth between getting larger, and much smaller. So this is, there are various problems if you just naively try to adapt the construction, but this seems to be the biggest one. And so the other smaller solutions can be, the other smaller problems can be solved kind of by modifying the starting group of monomials that you want to start with. But the solution to this third problem is a little bit more drastic. But ultimately, what happens is that we just won't allow infinite sums of monomials that are very close together. So let G star be the full starting group of monomials, which includes G, and then the solutions to the problem with the logs and the small elements of G is just to modify the starting group of monomials to include some logs and some exponential terms. So now our group G star is a little bit complicated, but we can formalize what it means for two elements of G star to be close to each other, and that will give us an equivalence relation. And then we define this modification of the Hahn series field to be the ring. We won't have a field whose elements are sums with reversible ordered support, but also with the additional condition that for each class, the set of monomials from that class that appear in each sum, this should be finite. So we really are just ever preventing ourselves from having infinite sums of monomials that are close together. But because we're restricting some types of sums to only be finite, that's why we don't get a field, right? So because to invert those kind of things, you might need to have an infinite sum, which we're not allowing. So this modified Hahn series construction, K of G subscript tilde, it can be ordered by just take some sum, find its leading class, that will be finite. And so it can be ordered by the lemma from the previous section, as long as we start with X and K that will satisfy our assumptions. So this will give you an ordered ring. And that's, so here I write, so that's our stage 0. Just to compare, in the usual logarithmic exponential Hahn series construction, their stage 0 is this thing, the Hahn series field coefficients in K. The monomials are just powers of X. And so from there, they add in more and more monomials for X of different things, and then build an exponential field. So we'll do something similar. I won't write it out, but essentially starting from this stage 0 field, we'll kind of use this this modified Hahn series construction over and over again, add exponentials of new larger things. But what we will end up building is only an ordered ring with a partially defined exponential function. And that finishes the adaptation of part 1 of the transseries construction. So now we need to figure out how to adapt part 2, which is the self-embedding, where you try to close off under log. But we'll also hope that maybe we can somehow close off under X and multiplicative inverses too. So just to indicate how you would, what you might do instead of having a self-embedding map, I have a few examples here. So let me start with example 2. So what happens if we want to try to exponentiate this element E of X over E prime? Well, E prime is bigger than E, so E of X over E prime is going to be an infinitesimal. So we should exponentiate it by using the power series for E. But the issue is that E over E prime is actually going to be a large, so such a large infinitesimal that any powers of E prime over E will be equivalent based on our closeness equivalence relation to E over E prime itself. And so that's bad because that means we can't actually take an infinite series like this. So this is not allowed. In our part 1 construction. So maybe we would hope to find the exponential of this element somewhere else in some other kind of field into which we can embed the one that we just built. So similarly, if we try to look for a logarithm of e of x, well, using the difference equation for e, that should look like e of x minus 1. Now just, I forgot to write. So going back to example 2, I'm sorry, I'm jumping around a little bit, but e of x over e prime of x, we can use the difference differential equation for e prime to say that this should look like e prime 1 over e prime of x minus 1. So we see this x minus 1 here, we see this x minus 1 here. And in example 3, where we're trying to find a multiplicative inverse of e prime plus e of x, we have this same issue trying to take an infinite sum of these things, which is fixed by thinking of taking infinite sums of instead 1 over e prime of x minus 1. So what I'm getting at here is that in this construction that we built from part 1, there are all these things that we're missing, like the log of e and the exponential of e over e prime and the multiplicative inverse of e prime plus e. But we can see those elements if we had, instead of starting with things composed with x, we started thinking of them as x minus 1. So if we had instead built our part 1 construction with these shifted monomials. So this is not a proof, but the idea is it just to give a little bit of justification for what we'll end up doing to adapt part 2 of the construction. So let x minus m be x shifted by the elements of x shifted by m. Let k, x sub x minus m, be the ring that we built from k and these shifted x's via the adaptation of the part 1 construction. And then each of these rings will embed into the next one. And every element here, if you follow a finite sequence of embeddings, every element will have a logarithm, it will have an exponential, and it will have a multiplicative inverse. So if we take the direct limit of this system, we can call this dx of k, then this is going to be an ordered field with a totally defined exponential function, logarithm, and also closed under restricted analytic functions. So this is not obvious. I just wanted to do these 3 examples to try to convince you that this is indeed what happens. But there are a lot of things to check to make sure that this does work. Okay, so in this in our part 2 construction, we adapt the usual logarithmic exponential transseries. We have to deal with these problems that come up, particularly this third one. And then the way that we fix this third problem causes a bunch of new problems, like only ending up with a ring and a partially defined exponential function. But then we can fix those issues in our version of part 2. So we do, in the end, get a field that's ordered and that's closed under exp and log and restricted analytic functions. So now the final part of the construction is to actually build the full field of sublogarithmic transexponential series. So we'll start with just the regular exponential logarithmic transseries. So let f0 be that, and we'll define an equivalence relation on f0 by you take 2 elements, and if their difference is finite, then you define them to be equivalent. And so now, what's the idea for how to build f1 from f0? Well, the finite subsets of the positive infinite equivalence classes, those will form a directed set. And for each finite subset, we're going to build a field using the construction from part 2. So given some finite subset of positive infinite equivalence classes, let alpha 1 be the smallest element of that finite subset. And then pick x alpha 1 to be a set of representatives from alpha 1 that's maximal, satisfying the assumptions that we talked about earlier. And then we run the construction that from part 2 to build the field, starting with our X set is going to be X alpha 1. And then our field of coefficients is not going to be exactly K, but it's going to be something a little bigger than K. Okay, so now take the second smallest element of your finite subset of positive and infinite equivalence classes. Let X alpha 2 again be a set of representatives from alpha 2 that's maximal, satisfying the assumptions from earlier. And now we're going to build a field. Our X set will be X alpha 2, and our field of coefficients will be the one we just built. Okay, so now go to the third smallest element, continue. So for each finite set, you build a field using this construction from part 2. These will all embed into each other to form a directed system. And you take F1 to be the direct limit. So that's how to build F1 from F0. And then you want to build F2 from F1 in the same way, F3 from F2, and so on. And these fields will all embed into each other. So again, we can take a direct limit. And this M sub K because that was the initial field of coefficients we started from, is going to be our order field that's closed under all the symbols of the transexponential language. It has a derivation that works like differentiation with respect to the variable of the field. And it's built all along the way so that we only ever build things when we know that the ordering we define on them matches the true ordering that comes from germs of functions. So the field of germs of LE terms should embed into this MK. Okay, so that's the full construction. I guess I have a couple of minutes left. So I can answer questions, or I can go back and explain a little bit about these other problems that arise in the second part of the construction when you're trying to adapt the usual log X series. Yeah.
So I have a somewhat quite, I don't know, maybe I missed the point somewhere, but yeah, it's right there at the bottom of the screen right now, right? So you're using the iterated derivatives of E as generators for the monomials, right? But as terms of functions, some of those monomials tend to be equivalent. That's what you're showing there. But then in order to determine the order between those series, you use Bosher-Nitzan's iterated logarithmic derivatives instead. And so why not just use those as the generators of monomials instead?
Yeah, that's a really good question. And so I did try that, and the reason why it won't work later on. So here in this part where you're trying to order things, it actually, let me go back to it. Using these just makes the ordering a lot easier, right? But this closeness, this way that, or sorry, not that, this closeness here, that the monomials are somewhat close together, that actually is a benefit. That's what allows us to know that we can make this assumption on the x's, that we're starting from the same level of exponentiation of everything. The reason why Bosher-Nitzan sequence of functions are so easy to order is that they're all like stratified among different levels of exponentiation.
Right, they're very, very far apart.
Right. Yeah. So the closeness actually is a good thing later on.
So you're saying that you wouldn't get enough monomials if you were just using those iterated logarithmic derivatives?
It's that so I the most obvious thing to me that would go wrong, and it's actually something I didn't mention, but solving this problem is what gets really difficult if you use the like iterated logarithms, because it's actually hard to determine what log of one of those iterated logarithms should look like.
Right. So yeah, maybe it is true, right? Maybe there is just not enough. There wouldn't be enough monomials to go around.
Yeah.
Okay. Well, okay. That's a good reason. Thanks. Are there any other questions, or would you like to? Well, it's 11 o'clock, so I guess. Yeah. Are there any other questions?
Yeah, I have one question. Like, do you know how this, your construction compares to the others? Like, do you know if you can embed your version into the hyperseries, for example?
So I think in order to know if you could embed my construction into the hyperseries, you would need to know how to define a derivation on these fields. And I think that is actually quite a difficult thing to do. So I guess the answer is I don't know. But I think maybe not, it's not possible with what we know about these hyperseries at this time. And then you can't embed the other way because the field of series that I build is much less complete than these hyperseries constructions. So it's just much, much smaller.
Thanks.
I also have a question. Sorry for the noise. Thanks for the talk, by the way. And I wonder if your field MK is an H field. In the sense of,
that's also a good question. I haven't thought about it. Yeah, I'd have to. I'm not so familiar with H fields. I'm actually looking forward to attending the Laos class to learn a little bit more about them. But that would be an interesting thing to check, whether it is an H field.
Okay.
Well, if it is a Hardy, if it's a Hardy field, oh yeah, the MK here is a formal field, right? And
It's
the field
larger.
of germs, of course, is a Hardy field, I suppose. And so it would be an H field, but the MK itself, that's another question.
Mm-hmm.
Yes, and maybe I have a follow-up question. Did you think about doing the same thing for the transfinite iterate of E, of
No,
a large E, or stuff like that?
I haven't, and I think does that have a difference equation? Because I think you need some kind of grasp on the function to be able to do this construction that I've done.
Yes, I was thinking of the same difference equation where you replace X by E.
Oh, okay. No, I haven't thought about that.
Okay.
It could also be interesting, but my sense is that it would be harder.
Okay, maybe not. I mean, those are basically the same. Yeah, maybe not.
Maybe not. I think you wouldn't get the same. It's nice that you get these. Going back to the top, these algebraic differential equations for the derivatives of E, which you wouldn't get if you replaced X with E here. I don't think.
Well, you would, but there would be some e's. I mean, there will be some big, larger E, and then some E, and then it would be more complicated. I think. Maybe I have a third question. Yes, so just how far are you from being close for under composition on MK? I mean, is it really not close under composition, or is it almost?
I don't think I'm close, and so kind of because this thing about only allowing some finite series is needed to make this construction work. I think that really makes I don't know if it makes the composition impossible, but it makes it like quite difficult to figure out how it would work. I think it's just too small maybe to be closed under composition. But I would have to think through that more.
Well, I'm guessing the problems you already had with logarithm, like they repeat for all compositions.
Yeah, I think so.
Yeah. All right. Well, thank you very much for this very nice talk.